Hello. Thank you very much for the introduction. It's very, very special for me to be here today because it's actually exactly 10 years since my first ADC talk at the first ADC, which was back then called Juice Summit. So I put on the same T-shirt I was wearing 10 years ago to celebrate the occasion. I have a little bit less hair, but I think that's fine. Um, and yeah, it's kind of mind-blowing to me. 10 years ago, I was there when we started this whole thing, and I was quite heavily involved in organizing this event for the first few years at least. And the mind-blowing thing is that 10 years later, it did grow from this one idea that a bunch of us had. Wouldn't it be nice if something like this would exist to now being, the most important international event for audio developers? So it's really mind-blowing how this was happened and was so successful, and I'm very, very happy about that. And so even though I have actually not been working in audio or music software for quite a few years now, I'm doing fintech at the moment. I just couldn't miss this for the world. I would just had to be here 10 years later and give a talk. So I'm here, and I have a talk about memory order for you. And I hope you will find it interesting. And memory order is something that I found really confusing throughout my own career, and it crops up in like any kind of environment where you need to do log-free programming or rely on log-free algorithms or data structures. And of course, this happens in audio, right? So in audio, we have this scenario where you have one real-time thread that must not block, right? And that's going to do the audio processing. And we have one or more other threads that are doing non-real-time things like rendering your GUI or MIDI I/O or file I/O or networking or whatever. And turns out in many, many other areas outside of music tech, you also run into very, very similar problems. And there you always have this issue that you have to somehow share data between those threads, but you can't use locks. And so then you end up developing log-free algorithms. And I talked about a bunch of these over the last few years. I had a talk last year here about C-clock, and me and Dave and Fabian and other people had lots of talks about other data structures and algorithms. Of course, the log-free queue is a very popular one, which Dave was talking about yesterday. Very good talk. Thank you, Dave, again. But the common thing in all of those algorithms and data structures is that you rely on the same building block, which is atomic. So who here is familiar with atomic? Okay, that's almost everybody in the room. That's great. So you all know the interface of atomic. It has these operations, right? You have load, which is how you read an atomic variable, and you have store, which is how you write one. And then on the right-hand side, you have a bunch of read, modify, write operations that can do more interesting things. And then some of these operations have this short form, which is defined in the standard via these operators. And so what you can do, you can either use the long form. For example, here you have you're loading an atomic variable A, and then you're storing, you're reading, and then you're writing a value to it. So you can either use the long form with load or store, or with these operators, you can actually basically write it as if it was a normal assignment, or for example, if you want to increment it by 1, you can either write the long form and you write fetch add 1, or you can just increment. So that's kind of the short form, and that's what these operators are about. But I grayed them out actually because I do not recommend anybody to use this short form ever. And it has 2 reasons. One reason is that if you use the long form always, it kind of makes it obvious that this is an atomic operation. This is not just reading or writing an int or a float, which is kind of important to see if you see the code. And there's another reason, which is actually also really important, but less talked about. And that is what we're going to talk about here today. So let's look at this kind of very classic, very simple, basic use case. We have a very simple audio plugin with a single gain knob. And then the gain is, we have some kind of like knob, and then the gain is represented with a float, which is just a member, data member here. And this is oversimplified slideware code, but you all know what is going on here, I guess, to any plugin developer. This shape should look quite familiar. And so we have here kind of a knob on value change callback, which gets called whenever the user wiggles the knob. And then the gain gets set from the value that the knob has in the GUI. And then below that is the process function, which is going to be called on this real-time thread, which does some audio processing. And then it basically just multiplies the audio data with that gain to make it louder or less loud. So that hopefully looks very familiar to any audio plugin developer. And there is, of course, a bug here. Who can tell me where the bug is? Yeah, over here. The gain variable is not atomic. And what does that mean? Yes, it means you have data races and undefined behavior. Exactly. Thank you very much. And so what do you do in order to not have a data race and undefined behavior here? You make it atomic, right? And so now we can write the long form to make it really obvious that we have thought about this, and these are atomic operations, and now we store the gain from when we wiggle the knob, and we load it in the process function, and now everything is fine. And the second reason why I recommend to always use the long form is that in the long form, you can actually specify the memory order, and the memory order is an extra parameter that every single atomic operation has. And it turns out that if you don't specify the memory order, you are probably not doing it right, because this is the only way you can get your algorithm both correct and performant. And we're going to look at this in the rest of the talk. So if you use the long form, you can just add a second parameter, and that's going to let you specify the memory order. All right. So let's look at this memory order thing. And in order to understand what this is and what this is for, we need to, I want to do it in a particular way, because the reason, and I'm curious if anybody else had this experience, the reason why I always found it very confusing is because I saw this memory order thing, which is there. It's a parameter, right? And I was like, okay, what do I put there? I don't know. And then I look into the specification, for example, CPP reference, right? And CPP reference describes, what memory order does, and it describes all these memory orderings, and it's just so complicated and it makes absolutely no sense. And I was reading it over and over again, and I was like, I don't know what that is. And so what I don't want to do today is to kind of just repeat that and describe to you, what the specification actually says, because that's going to be very confusing unless you already know what it does. Instead, I want to kind of do some kind of a more intuitive, more kind of maybe oversimplified description, but instead of getting exactly across like what is in the specification, I want to get across a feeling for why is this actually there? Like, what problem is this actually solving? Like, what do we need this for? And why does it make sense to have these different options and to specify them? And again, glossing over like some of the kind of technical details, but just giving you a feeling for what this actually is and why it's there. And I think with that knowledge, you can then go and see other talks that go into more detail, and then go and read the actual specification, and hopefully then it will make a little bit more sense. So this is kind of the idea for today, kind of a more introductory talk into this topic. And so in order to really understand what this is and why it's there and what it's for and what problem this is actually solving, it actually makes sense to actually ask ourselves, why is this a data race and why is this undefined behavior? Right? Why is this a problem? Because if you look at the assembly code that's generated and like how CPUs work, it turns out that there are no magic atomic read or write instructions on the CPU level. Okay, like if you go to like read, modify, write operations, they're a little bit more magic. But if you talk about just loads and stores, you're just reading bytes or writing bytes on a hardware level. There's no magic atomic or non-atomic. You're just reading bytes. So why is this whole thing even a thing? Why is this undefined behavior? Why can't we just write the bytes and just read the bytes, because that's what the machine actually does, right? And so understanding this is key to understanding why memory order is there and why we need it. And so one thing that you hear often, including from people on the C++ committee like myself, is that if you have undefined behavior like here, then a dragon can emerge from your laptop and burn your room to the ground, because undefined behavior can do anything. And this would actually be behavior that's conforming with the ISO C++ standard, right? This would be conforming behavior if this dragon emerges from your laptop. But really, it isn't really like this. It's not like undefined behavior is there so the compiler can go and say, ha ha, you did something bad, I'm gonna punish you for it, right? This isn't really what this is about. And so you won't actually get a dragon emerging from your laptop and burning your room, right? This is not what's actually going on. So why is a data race undefined behavior? And there's a few reasons. And one is that we have optimizing compilers. And actually, I should say, undefined behavior didn't start out like this. Undefined behavior, when you look at the beginnings of C++ in the 80s, or even go back further to C, it started out as this thing of different hardware architectures, and there was, 70s and 80s, which was much more wider variety of different hardware architectures than is mainstream today. It was kind of there to say, well, different hardware will do different things. Like, for example, signed integer overflow. Yeah, different CPUs would handle this different ways. Some would wrap around, some would trap, some would do something else, depending on how integers are represented in hardware. And back then, there was like a much wider variety. Like nowadays, kind of it's all two's complement, but it wasn't like this in the past. And so undefined behavior originally was put there to say, well, hardware might do different things. We don't want to specify that in the standard. But then it turned out that people want performance, and then compilers started exploiting the fact that things are undefined to treat that as something that you can assume will never happen, and then optimize on that assumption, right? And that's how you get your code fast. And so then undefined behavior developed into this other thing, which is what it is today. And so compiler optimizations today are very, very sophisticated, and they can reorder or relide any operations or do other clever things. And this is called the as-if rule in the C++ standard. As long as the observable behavior of the program is the same. And the observable behavior means the observable I/O, right? Like stuff that's printed or other side effects that are happening that you can observe outside of the program. That's what we mean by observable behavior. Like writing to an audio buffer, right? That's observable behavior, for example. And as long as that observable behavior is the same, the optimizer can do to your program whatever it wants and reorder elide operations, exchange them by different operations that have the same effect. And it does all of these things, assuming that no undefined behavior happens. And in this case, the undefined behavior is data race. And the compiler will just assume that no data race will ever happen. So for example, if you have code like this, where you have some kind of integer flag that comes from somewhere, it doesn't really matter, and then you have a loop, and inside the loop, you check the value of the flag, and if the flag is not 0, you write some number into this data buffer. It doesn't really matter what's going on here, but if the compiler sees this code, it can go and say, hang on a minute, so you're checking this flag every single time inside the loop, but you're not modifying it, right? So it's always going to be the same. And now I can assume that there is no data race, and I can assume that no other thread would also modify it, right? Because that would be UB, so that can never happen. And so I can assume that flag is not actually going to be modified here and move this whole check out. Just check the flag once, and then get out if it's 0, and then just not worry about this flag at all, and just blast through the data in the loop, and it's going to be much faster because you don't have to check this flag every single time. And this is a transformation of your code which under the as-if rule is allowed. And so every modern compiler will do this optimization and many, many other optimizations like this. And you depend on these optimizations happening in order for your code to be fast. Now, if this was our only problem, if the only thing we were fighting was the optimizer, there is a way to prohibit this without using atomics and all of that stuff, which is volatile. Exactly. So if you put volatile in here, which people are doing, it's not what you should be doing, it's not correct, it's still undefined behavior. But if you put volatile there, you do actually prevent this optimization from happening, because then the compiler can no longer assume that the value of flag is not going to change. And so if you have for example, an embedded system where you know that you don't have a data race within your program, but the value of this flag might change from outside of your program, then this is fine. And if you have a program where you might have a data race inside your program, but you're running it on a desktop machine from 20 years ago, you will probably also be fine. However, you will most certainly not be fine on any kind of modern desktop or phone, right? Which is why volatile is not the solution here, because you're not just fighting the optimizer, you're also fighting the hardware. Because also the hardware can also do these optimizations. And this is like long after like your CPP code has been compiled into an executable and it's running on the CPU. And modern CPUs take it apart into micro instructions, and they reorder them. They do very, very aggressive store buffering and all kinds of other magic that happens in the hardware. And so your program actually gets modified inside the CPU. For example, if you have something like this, where you have an integer and it's reading value from one memory location, and another integer reading a value from a different memory location, and then you do something with those integers, and then you have other code that does something else unrelated to that. And then the compiler, sorry, not the compiler, the CPU in hardware can see, well, actually this memory location is not in cache, right? So if I execute this stuff in this order, these instructions, then I will get a cache miss here. And then before I can execute the next instruction that adds these integers together, I will have to wait for that that value of j to be fetched from main memory, which is 200 instructions. So I'm going to just stall for 200 instructions, and that's a waste of time. So what I'm going to do is I'm going to reorder all of the stuff that happens afterwards to before, so I can do this, while I'm waiting for that data to be fetched from main memory. And that happens in hardware. And again, that assumes that no data races are happening. And there is actually a third thing, which is even more interesting here, which is beyond the CPU, you have a cache, and you have multiple CPUs, and you have multiple caches. You have shared caches, you have exclusive caches, you have all of this stuff. And in order for these caches to work correctly, modern hardware implements coherence protocols, cache coherence protocols. And those things can cause different threads to observe operations happening in different order, or not at all. So if you have, very oversimplified this kind of architecture where you have multiple cores, which is the case on every modern computer and every modern mobile device, right? And then you have some shared caches, exclusive caches, and then you have complicated in-hardware algorithms that make sure that all of these caches and cores agree on what the values of the data are. And so there are many, many different cache coherence protocols like MACI, MoACI, and all kinds of other things. This is like a whole talk in itself, how this works. And a lot of this is also like, if you dig a little bit deeper, it's actually proprietary. Like CPU hardware vendors, they don't disclose exactly how all of this works, and it works vastly differently on different architectures, and even on like different generations of the same kind of architecture. And so these cache coherence protocols kind of make sure that different cores agree on what's going on in your memory, because otherwise everything would just fall apart. But importantly, all of this cache coherence stuff in hardware only ensures per address consistency of each individual memory location, right? Or in practice, it's going to be each individual cache line. So that different cores eventually agree on what the value of one given memory location will be after everybody's done writing to it. But it does not ensure a consistent order of operations on different memory locations, right? So different cores might see operations happening in a different order depending on what the caches are doing, right? And so for example, one write to a variable on one core might end up writing this to the L1 cache, but not in the L2 cache, until something else happens on a different core, right? And so the other core is just not going to see that write until later. And so, for example, if we have code like this, which this is going to come up again, it's kind of this very simple example of a pattern that happens often in log-free code. So you here have some kind of data, and this is int, and now I put volatile in there just to make sure that we're not messing with the optimizer here anymore. The optimizer is not a problem here. We're talking about hardware and caches. So here we have basically one thread, the first thread, which is writing 42 to this data integer, and then setting a Boolean flag saying the data is ready. And then the other thread basically loops, like spins on this like ready flag, and when the ready flag says now the data is ready, it's going to read the data and it's going to assert that it's actually read the correct value here. But because this is not atomic, this of course doesn't work. And again, this is not about the optimizer. This is about caches and multi-core architecture. So for example, what can happen is that core 1, which is executing thread 1, can say that, okay, I'm writing 42 to data, but I'm not going to publish this write in the cache that is shared with core 2, right? For whatever reason, that's not necessary right now. And I'm going to now write true into ready, and I'm going to publish that write into the shared cache. And then I'm going to publish the first write maybe at some point later. So thread 2 might see those writes happening in the reverse order. And then, of course, everything falls apart. And thread 3 on the core 3 might see them in the other order, right? You just don't have any guarantees. And so you have to deal with this. And how do you deal with this, right? So there's different ways you could deal with this. You could say, okay, there's all of this reordering happening, and you don't really get any guarantees about like different memory locations happening, writes to different memory locations happen in a different order. And now you have a log-free algorithm where it would just break. So you have to somehow tell the compiler, but also the hardware, don't make these assumptions. Please don't reorder my reads and my writes to this variable. And there's different ways of doing this, right? You could just say, I'm just going to use atomic with like the default, and I'm going to just impose a consistent order of all of these operations across all cores. And this is the default. And turns out that's actually really, really slow in many cases. So you kind of get the correctness, but you also pay a hefty performance penalty. And in some cases, or in many cases, that's kind of not what you want to do. The other extreme is you could say, okay, well, I have my log-free algorithm, and then, please, hardware architecture, please don't reorder this specific thing. Please publish this read or this write into the shared cache at this point, and go like very, very granular. But it turns out you can't really do that either, because that is very, very like hardware specific, architecture specific. It's not portable. And so memory order kind of provides this abstraction. It says, okay, well, there's all of these different hardware architectures, there's all of these different ways these caches can be organized. I'm just going to put an abstraction layer on top of this and give you a few common options, like common kind of trade-offs between performance and correctness that are useful for many different use cases and that map to reasonable things on all of these different hardware architectures, right? So that's what memory order is. It's kind of this abstraction layer on top of all of these different hardware reordering things in the CPU and cache coherence protocols and all of that stuff that gives you a handful of reasonable options they're gonna map to something reasonable on all of these hardware architectures, and that give you different options and let you select different trade-offs for your algorithm without being too granular, right? And so the options that we have in the C++ standard today are these 6, and it does look a little bit scary because 6 is quite a lot. Turns out in practice it's actually 5, because consume was standardized back for C++ 11, but then it turned out it's not really something people know how to implement in hardware. That's not really how hardware works. So that one turned out to be less useful than we thought, and so it's actually now been deprecated, and it is not actually implemented on any hardware, so it's not really going to do anything useful. So just pretend this doesn't exist. So we're left with 5. Still a lot, but turns out 5 is actually 3, right? So actually we have really just 3 options. First option is relaxed memory order, and this is kind of the least restrictive and the most performant. Second option is acquire release memory order, and this is, as you will see, the one that you kind of end up using the most. And so there are 3 enums, but the way this works is that basically acquire goes to read operations, release goes to write operations, and acquire release goes to read modify write operations, but it's kind of the same thing. And then option 3 is sequentially consistent memory order, and that's the most restrictive, and that is also the safest, which is where it's the default, but it's also the one that's the slowest and the one that you actually almost never need because it provides more guarantees than you typically need. It's actually very rare that you actually do really need sequential consistency. So let's talk about all of these. And so relaxed is interesting, and I heard some people say relaxed is the most complicated because it's so hard to reason about. I actually think relaxed is the simplest and the easiest to reason about. So what relaxed gives you is it says that if you have one atomic variable, let's call it B, and then you have access to that variable, and then you make that relaxed, then access to that variable can happen concurrently from multiple threads. So it's no longer a data race to read and write from that atomic variable from different threads, which is kind of the main point of atomic. And also reads and writes to that atomic variable are guaranteed to be observed in a consistent order. So all threads are going to agree on the order in which reads and writes are happening to that one variable B. However, a relaxed atomic operation does not impose any memory order on any other operations on any other variables, atomic or otherwise. And so this makes relaxed the perfect option for the use case that we saw at the very beginning of the talk. So if you just have one single atomic variable like the gain, and you don't really care about how this is ordered with respect to anything else going on in your program, you just want different threads to be able to read and write to gain concurrently and to agree on in which order those writes happen so that you don't get inconsistencies in the gain, right? So then if one thread writes to gain in a smooth fashion, then another thread sees those writes in the same order, right? So you kind of, that's the guarantee you want here, but you don't care at all about how this is ordered with respect to anything else in your program. And whenever you have a use case which is just about a single atomic like this, relaxed is the correct thing because it gives you the one guarantee that you want. It doesn't give you any guarantees that you don't need, so you get maximum performance, right? So this is when you use relaxed. However, if you need more guarantees, if you have something where you do rely on other things happening in your program and how those things are ordered, then you run into problems when you use relaxed. And we can now look again at this example that we also had earlier in the talk. So we had one thread that is writing 42 into this data integer and then sets a Boolean flag saying the data is ready for reading. And then another thread waits until that flag is set and then reads the data and asserts that the data indeed has the correct value, okay? So what happens now if we make those atomic variables relaxed, those atomic reads and writes relaxed? So we don't have a data race, right? We know that, not at least on this ready flag. But we do not have any guarantee about how other operations, atomic or otherwise, are ordered with respect to this ready store and ready load. So what the optimizer or the CPU or the hardware could do is it could reorder reads and writes to ready with respect to any other reads and writes. So it could, for example, move the write to the data down to below the ready store. Or actually, this is not really about okay, when you talk about the optimizer, it's about physically moving the instructions, and that can also happen in a CPU. But when you talk about the cache coherent stuff, it's not so much about reordering them, but in which order do other threads see those reads and writes, right? And that kind of depends on how these operations are published across this cache hierarchy. So it's when I say reordered, I mean either that or in which order another thread might observe those operations, which is not necessarily the same order in which they happen on the first thread. So if this is relaxed, another thread could observe the data write being after the ready store, right? And also, thread 1 could observe this assert happening before here. And so then when you do this, you again have a data race, right? So you don't have a data race on ready, but you have a data race on data because one thread writes to data, another thread reads from data, and you have no guarantee about them not happening concurrently because they can be reordered arbitrarily because it's just a relaxed operation on a different atomic. So you could fix the data race by making data also atomic, right? And now there's no data race anymore, but you still don't have a guarantee that this assertion is actually going to succeed. It can still fail. So you don't have a data race, but you're still incorrect. And so in this case, when you have different atomic operations on different atomics that need to happen in a particular order, that's when you use acquire release. And in order to understand acquire release, we do need to dive a little bit into the C++ memory model. So this is actually how this is specified in the standard, and I'm going to keep this short, not dive too deep. But these are kind of some very essential definitions that we need. So two expression evaluations conflict if one of them modifies a memory location and the other one reads or modifies the same memory location. And a data race is when you have two conflicting operations, at least one of which is not atomic and neither happens before the other. And this happens before is a word of power, it's like a term of art in the standard. And when you have that, then you get a data race, and that's undefined behavior. So what does this happens before mean? An evaluation A happens before an evaluation B if either A is sequenced before B or A synchronizes with B, and then this is also transitive. So sequenced before B is kind of the simpler one here. This is about stuff that happens on a single thread. And so I'm not going to go into exactly all of these words here, but it means basically that if you have a single thread, then things happen in a certain sequence there. So for example, if you have a single thread and you call f with parameter 1 and f with parameter 2, then because you wrote them in that order, the call to f1 is sequenced before the call to f2, right? However, if you now do those operations on different threads, then f1 and f2 are unsequenced with respect to each other, right? And so you have a data race whenever you have conflicting operations and neither is, and they're not sequenced with each other and they're also not synchronized with each other. So what does that mean? So A synchronizes with B if an atomic operation that performs a release operation on one atomic object M synchronizes with an atomic operation B that performs an acquire operation on the same atomic object M. And so what does that mean? If you have an atomic store operation with memory order release, and then an atomic load operation on the same atomic with memory order acquire, then those two synchronize with each other. And then you get the guarantee that you need. So if you go back to the code here, if you have a store of ready on thread 1 and a load of ready on thread 2, and we use release for the store and acquire for the load, and it's the same atomic variable that this is on, then the store synchronizes with the load. And so then, because everything that is kind of written before this store is sequenced before the store in thread 1, and everything that is written after the load is sequenced with that load in that thread, and now those synchronize with each other, you actually get a guarantee that everything below that load in thread 2 happens after everything above the store in thread 1. And this is exactly the guarantee you need to make this work. So that means if the store happens and then the thread does the load, it might not see the store, right? You don't know that. But if it does see the store, it also reads everything that happened before it in the other thread, right? So it might observe anything that happens after the store as if it happened before, so things can get ordered up the store, but it cannot observe this write happening after the store. So things can be ordered up the release operation, but not down. And on the other thread, it's exactly the other way around. Stuff can be ordered down, but not up, right? And that's the guarantee you get with acquire release, and that makes this not a data race and also correct, even though data is actually not atomic here. That's also important. Data is not atomic, but you still get this guarantee. There's no data race, and it's also correct. All right. So yeah, that assert always holds. And so we're almost done. There's just one more thing, which is if you do this in different algorithms, different data structures, and if you see all of these people doing talks about different complicated things that use this stuff, there's one other tool that you kind of need, which is fences. And fences are useful when you have many, many atomic operations at the same time. And this is an example from a talk that Fabian Ren-Giles gave a couple years ago here, called I think, Real-Time Confessions. Yeah, that was a very, very good talk. And so this was a particular data structure from this talk. And it doesn't really matter exactly what this does, watch Fabian's talk. This is really not important, like how this actually works in detail for the purposes of what I'm trying to explain. What matters is here you have a bunch of atomic operations that synchronize with each other, but here you have a whole buffer of them. You might have like 1,000 atomics, right? And so on the right-hand side, actually, he's using a read, modify, write operation, so you get acquire, release. But that don't worry about this. This is just because the algorithm is constructed in this way. Just pretend it was, store, release on the left and load, acquire on the right, because that would be the same for the purposes of how fences work. So just pretend that was the case. And so this is correct, but it's going to be slow because now you have 1,000 atomic variables, 1,000 atomic stores on the left, having to synchronize with 1,000 atomic reads on the right. And so there's a lot of atomics that have to all synchronize with each other, and there's a lot of constraints you're putting on the program. But it turns out you don't actually need quite that much. You just need basically this entire loop to synchronize with the entire other loop. But you don't care about the individual atomic operations in the loop all synchronizing with each other, right? So you just need the entire loop basically to synchronize in a way that everything that happens before the loop synchronizes with everything that happens after the other loop and the other thread. Is that clear? Does that make sense? And so the way to do this is instead of putting acquire release on every single atomic operation, you make those relaxed and you put a single fence, a single release fence below, like this loop on the one hand, and a single acquire fence before the entire block on the other side. And then, the individual atomics can be relaxed. And what this gives you is, and this is kind of glossing over the details, but like it's a release fence is kind of upgrading all of the atomic operations before it to release operations as a whole. And the acquire is kind of upgrading all the atomic operations on the right-hand side to acquire operations as a whole, right? And so that means you do get the guarantees you need without having all the individual atomics all synchronized with each other, which is going to be more expensive. And Dave had another example of this in his talk yesterday, where there was the same thing going on, where you had a bunch of operations on the left and a bunch of operations on the right, and you kind of want all of them to synchronize with all of the others as a block, but you don't need the guarantee that they all synchronize with each other individually. And this is when you use fences. And that lets you squeeze out more performance, because then the individual atomics can be relaxed and you can still enforce exactly the guarantee you need on the level on which you need them. And basically this kind of mental model of acquire release, this is what you most often end up using for your algorithms. But then there's also the third option, which is sequentially consistent, right? And what sequentially consistent does is it gives you more guarantees. It basically says that all atomic operations basically all synchronize with each other, which means that all threads are going to agree on the exact order of all atomic operations in your program that are sequentially consistent happening in a particular order, right? And this is the default because this is the safest thing. This is the thing that is going to make your algorithm correct in most cases. But it's also the slowest one, right? And it turns out that you almost never need this. And in fact, in my entire career, I haven't encountered a single real-world use case where you actually need sequentially consistent. So it is the default, but it is pretty much never the thing you actually need. And doing any of the other options is going to be faster and just as correct for most cases. I had to dig in order to find an example where you actually do need this guarantee. I found one on CPP reference. And this involves 4 threads here, right? So you have 2 flags, X and Y. And then you have thread A that sets the X flag, and thread Y that sets the Y flag. And then you have thread C, which observes in which order these two stores happen and set and increment z when x happens before y. And then you have a fourth thread D, which also increments z if y happens before x, right? And so here we want to guarantee that at least one of those threads actually increments z, right? This is the assert in the last line. And so here you need to guarantee that thread C and thread D agree on the order in which thread A and B set those flags, so that either X happened before Y, and then thread C gets to increment Z, or the other way around, and thread D gets to increment Z. But you need to guarantee that at least like one of those threads, exactly one of those threads, got to increment Z. And this is an example where the assert will fail unless, or may fail sometimes, unless you use sequential consistency, because thread C and D otherwise may not observe these writes done by thread A and B in the same order. So this is an example where you need sequential consistency. It's kind of a contrived example. Again, I haven't seen a real-world algorithm where you need those strict guarantees, but they probably exist. And so there's one more thing, which is differences between hardware architectures. And so it turns out these three options of relaxed, acquire, release, and sequentially consistent map to real-world hardware in different ways. So we have this hierarchy, right, between these three options. So relaxed is kind of the most loose one, the most performant one, and then acquire, release is kind of the middle ground, and then sequentially consistent is really conservative, really slow one that imposes the most restrictions. And so we have this hierarchy for atomic reads and also for atomic writes, right? And it turns out there's different kinds of hardware architectures. And if you're on a strongly ordered architecture, then you get kind of a more conservative option just by default. For example, on 64-bit Intel, which is a strongly ordered architecture, all loads are sequentially consistent by default, just by the way the hardware is constructed. And all atomic stores are released by default, right? So this is just get this for free, right? So if you put relaxed on your atomics and you're on 64-bit Intel, then all the atomic loads are going to be sequentially consistent anyway, and all stores are going to be released anyway. And so in this case where we saw this thing where one thread was writing data equals 42 and then setting a flag, and then the other one was spinning on the flag and reading data, and then that would horribly break when it's relaxed, right? Because the hardware can reorder them. On Intel, that doesn't happen, because if you put relaxed, you will always get sequentially consistent loads and at least release stores. So that code on Intel, even if you put relaxed there, would work just because of how the hardware works. But then if you take the same code and then port it to ARM, it's going to break horribly, because ARM is a weakly ordered architecture, and there you actually have relaxed by default. And if you want anything stronger than this, sorry, not by default. If you wrote in the code no memory ordering, then you get sequentially consistent. But if you put relaxed, then you get relaxed, right? So in Intel, if you put relaxed, you get this. On ARM, if you put relaxed, you get relaxed. And then you have to put something more strong there, and then the hardware actually has to do more work, because the compiler has to actually inject particular instructions on ARM in order to give you these extra guarantees, and you do pay a measurable penalty performance for that. So this is the reason why porting stuff to ARM can horribly break, even if it worked for decades on Intel, because you didn't get your memory order right. So this is worth keeping in mind, that these effects are actually much more observable on a weakly ordered architecture than on Intel, where these bugs surface much more rarely. All right, so now I'm actually through with my material now. Here's my takeaway slide. So when you do any of the stuff, implementing log-free data structures, log-free algorithms, understand the C++ memory model, at least superficially, understand the different memory orderings and how they're different and how to use them. Always use the long form for atomic reads and writes, because that forces you to say that what you're doing. And also it gives you an opportunity to specify the intended memory order. And please always do that, because that forces you to actually think about the algorithm and what guarantees you need or don't need, but also that gives you better performance if you get it right. And so how to choose? Use relaxed whenever you're dealing with a single atomic in isolation. You don't care about how other things in your program are ordered relative to that, which happens a lot in audio code. Use sequentially consistent when you actually need full sequential consistency, which is almost never. And those rules means most of the time you'll end up using acquire release. And also remember that that's not on the slide. Remember that you can also use fences to batch these acquire release guarantees. And of course, if you do any of this, always measure whether that actually helps your performance or not. Actually, that's not the advice. The advice is don't do any of this, just use a library. But it's good to be aware of this stuff. And so I hope this is kind of a good intro, and now you can dig deeper. There is Herb Sutter's classic talk, which is from 2012, which was shortly after the C++ memory model was standardized. Atomic Weapons, it's a 3-hour talk that dives really deep into all of this. It also explains like exactly what guarantees the different memory orderings give you in like excruciating detail. Great talk. There is Dave Rowland's talk from yesterday, which shows you one use case where you want to have different block view queues and you want to think about how to specify the memory order correctly. And he has lots of benchmarks for what happens when you do different memory orderings there and how what kind of performance you get. When you start to put more relaxed memory orderings into your atomics and how that actually gives you a measurable performance boost. There's another talk by Christopher Fretz from earlier this year, which is actually really interesting because he wrote almost the same talk as I did here independently. Like I had no idea about his talk when I wrote this one, and he didn't know about my talk when he did his. They're very similar. However, he also does something very useful that I didn't do today, which is he shows benchmarks. So he has another kind of queue and says, okay, if you use this memory order, we measure this, and if you use this memory order, we measure this. And again, you see this like practical, measurable performance impact of different memory orders. So I highly recommend those. If you're a little bit more old school and you like reading books instead of watching talks, I have 2 recommendations for you as well. The classic, it's a little bit dated now, but I think still useful, is Anthony Williams' book about C++ concurrency, which gives you a very solid foundation about how concurrency in C++ works. And then actually my favorite book on this topic is not even a C++ book, it's a Rust book. It's called it's called Rust Atomics and Locks by Mara Boss. And this was the book that I read where I actually finally for the first time understood the memory model, because I tried to understand it for many years and I failed. I was like, this makes no sense, this is too complicated. Then I read this book and she just explains it so well, and I was like, oh, finally this makes sense. And it's ironic that this wasn't a C++ book, it was a Rust book. But turns out it was not really a Rust book. It was just a book about low-level concurrency that happens to have code examples in Rust. And it turns out that Rust has the same memory model as C++, so you can directly apply that to C++ as well. So that book, highly, highly recommend. And that's all I have. Thank you very much.